Hello guys, and thank you for watching this video lecture. In this presentation, I want to talk about overview of probability. So here are the topics: experiment, sample spaces, events, set theory, axioms, and probability properties. Let's start with the basics. An experiment is any activity or process whose outcome is subject to uncertainty. Although the word experiment generally suggests a planned or carefully controlled laboratory testing situation, we use this terminology here in a much wider sense. So the experiment that may be of interest is tossing a coin once or several times, selecting a card or cards from a deck, weighing a loaf of bread or something. Then we have something called a sample space S. This is simply the set of all possible outcomes of an experiment. For example, when rolling a six-sided die, the sample space is simply 1, 2, 3, 4, 5, or 6. The simplest experiment to which probability applies is one with two possible outcomes. One such experiment consists of examining a single well to see whether it is defective or not, right? So N or D. The sample space for this experiment can be abbreviated like N or D. It means N represent non-defective and D represent defective. And the braces are used here to enclose the elements of the set. Another would consist of observing the gender of the next child born at the local hospital. So we can say male or female. So this is the sample space for this experiment. In our study of probability, we will be interested not only in the individual outcome of S, but also in various collection of outcomes from S. We say an event is a subset of the sample space. For example, the event of rolling an even number would be equal to 2, 4, or 6. And on the other side, for odd numbers, it will be 1, 3, and 5. So when an experiment is performed, a particular event is said to occur if the resulting experiment outcome is contained in A. So we can also have compound events where we have more than one outcome. In general, exactly one simple event will occur, but many compound events will occur at the same time. So experiment here we have, consider an experiment in which each of three vehicles taking a particular freeway exit turns left or right at the end of the exit ramp. So in here, the 8 possible outcomes that comprise simple spaces are LLL, it means left, 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 right, left, left, and so on. There are 8 simple events: 1, 2, 3, 4, 5, 6, 7, and 8. So in here, we have set all possible outcomes. Then we can have simple events like LLL or LRR. Then we can have compound. It means, for example, we say the event that exactly one of the three vehicles turned right. So we have one here, and one here. So this is a compound event. Or, for example, we have B event. Here, at most one of the vehicles turn right. It means in here, no, 1, 1, 1, right? Or C, we say the event that all three vehicles turn in the same direction. this one, right? So in here for B, we say at most 1. It means 0 or 1, right? So 0 or 1 is this one. And C is the event that all three vehicles turn in the same direction. So all three turn in left or turn in right. Now let's study some relations from the set theory. Set theory is fundamental to understanding probability. We use concepts like union, intersection, mutually exclusive, disjoint events to describe events. So for example, complement of an event that we show by A prime is the set of all outcomes in S that are not in A. Okay, this is the first. Or second, we say A union B, it means the event consisting of outcomes that are either A or B, right? So all of them. Then for the intersection, we say both in. So this is or and this is and, right? And you can say or and, right? Or and. It means here only one condition must be satisfied, but in here both conditions must be satisfied. Then we have mutually exclusive or disjoint. It means the A and B do not have any common, right? It means their intersection is equal to 0. So something we show like this, right? This is A, this is B. Venn diagrams are useful tool for visualizing these relationships. Later I will explain them. Example here. For an experiment in which the number of pumps in use at a single 6-pump gas station is observed as here. So you can see here 0, 1, 2, 3, 4, 3, 4, 5, 6, and 1, 3, 5. A prime complement, it means if the total possible is 0, 1, 2, 3, 4, 5, and 6, so this is, you can say, as the universal. Then universal minus A, it means those numbers are here but are not here. So 0 is there, 1 is there, 2 is there, so only 5 and 6 are not here. So this one, we can say that A prime is equal to U minus A, right? Then we have A union B. It means all of A and B, and we do not repeat. So we will go for 0, 1, 2, 3, 4, and 5 and 6 come here. We do not repeat these two. And we say A union C. So 0, 1, 2, 3, 4, and 5 also come from here. So it will be 0, 1, 2, 3, 4, 5. Then here we say A intersection B. So 0 is not here, 1 is not here, 2 is not here, 3 is in both. So 3 will come to here, 4 is in both of them, 4 will come to here, 5 and 6 will not be included. Then we say A intersection C. So 0 is not there, but 1 is in both of them. So 1 will come here, 2 is not there, 3 is in both of them. So 3 will be here, 4 and 5 will be ignored. Then we say A intersection C complement. It means this A intersection C complement is U minus A intersection C. What is A intersection C? 1 and 3. It means whatever is in U except 1 and 3. So we go for 0, 2, 4, 5, and 6. A small city has 3 automobile dealerships, General Motors dealer selling Chevrolet and Buicks, and a Ford dealer selling Ford and Lincoln, and a Toyota dealer. Experiment is observing the brand of the next car sold. A and B. A is for GM and B is for Ford. Okay, B is for Ford here. So this is B, and this is A, right? Then A and B are called as mutually exclusive because the next car sold cannot be both GM product and Ford product. So we say these are mutually exclusive. It means they don't have any common element. So this is a Venn diagram. It's a kind of pictorial representation of events, and manipulation with events is obtained by using Venn diagrams. So here, for example, this is S or U, I said, universal or S, and this is A, this is B. So this part, okay, I will show here. A intersection B. So this part is called as A intersection B. It means the area that is common between A and B. Then we say A union B. A union B, it means all the area which belongs to both A and B, right? When we say A complement, it means S minus A. It means all this area of S except this area under A, right? This is because we say A complement. Then we say mutually exclusive. It means A and B do not have any common area. If we have three sets, A union B union C is all the area under control of these three sets. Then we say A intersection B intersection C is only this part that is common between three of the sets. Given an experiment and sample space, the objective of probability is to assign to each event a number that we call it as probability of the event A. This will give a precise measure of the chance that this event will occur. To ensure that the probability assignment will be consistent with our intuitive notations of probability, all assignments should satisfy the three axioms that we call axioms, or also known as basic property. What is axiom? It's a statement or proposition which is regarded as being established, accepted, or self-evidently true. It means anyway it is true. So the first one is the probability of any event is a non-negative number. So probability is greater than or equal to 0, not negative. Then the second one says the probability of the entire sample space is always 1. Okay, then we say for mutually exclusive events, the probability of their union is the sum of their probabilities. So probability of A union A1 union A2 union A3 up to AN is the sum from I to the number that we have, like N is here, then N will come here, probability of each one, right? Sum of them. These axioms form the basis for all probability rules and properties. Example is here. Consider testing batteries coming off an assembly line one by one until one have a voltage within prescribed limit is found. This example describes a probability model for testing batteries coming off of an assembly line until a satisfactory one that we show by S is found. Each battery can have two states. One is S and another one is F. S means satisfactory and F means faulty. The process continues until the first satisfactory battery appears. So we have event 1. It means this E1 is equal to S. It means the event that the first battery is satisfactory. So finished, because this is our condition. E2 means the event that the first battery is faulty, but the second one is satisfactory. And third one is the two first batteries are faulty, but the third one is satisfactory. And in here, we say the first three are faulty, but the fourth one is satisfactory. This process continues indefinitely. So we go for probability calculation. The probability of a battery being satisfactory is given as the probability of 0.99. The probability of a battery is faulty is simply what? The probability of faulty is equal to 1 minus 0.99 is equal to 0.01. Okay, so PE1 is 99%, right? Because based on this fact. PE2 is this one multiply this one. Then probability of E3 is 0.01 squared because 2 times here, multiply 99%. Then we go for the rest, right? So we can say that 1, because all of them will be 1, is equal to PS and all together. So since we are certain to eventually find a satisfactory battery, the total probability must be equal to 1. So then we can go for 1 is equal to PS for all PE1, PE2 up to PEN. Then all of them together should be equal to 1. This confirms that probability distribution is valid. If the experiment is performed n times on some of the replication that event A will occur, it means the outcome will be in the set A, and on others A will not occur. So NA denotes the number of replications on which A does occur. Then NA divided by N is defined as relative frequency. It means the number of occurrence of A divided by all occurrence. So we call this one as relative frequency, and we say it's occurrence of the event A in the sequence of N replications. Here is one example. Let A be the event that a package sent within the state of California for second day delivery actually arrives within 1 day. So this is our event A. Now we want to find out the relative frequency. So here, this is the number of package arrived. It means 1 package arrived, 2 packages arrived, 3 packages arrived, up to 10 packages arrived. Then here, we can see whether A occurred or not. It means A not occurred. It means a package sent within the state of California for second delivery actually does not arrive within 1 day, right? So I explain here how do we calculate the relative frequency. So here we can see that event A not occurred. Number of times that event A occurred is equal to 0. So 0 divided by 1 as the number of packages received is equal to 0. Then event A occurred, yes, occurred. Number of times A occurred is 1. Then total package is 2. So 1 divided by 2 is equal to 0.5. Next, we have event A occurred, yes. Number of times this occurred 1 time here, so this is the second time. So 2 divided by this 3 is equal to 0.667. For the fourth one, we say again yes, so it's 3, and 3 divided by 4 is equal to 0.75. In here, no. How many times it occurred is still 3. And we say 3 divided by 5 is 0.6. In here again, no. So it's still 3. 3 divided by 6 is equal to 0.5. Then we say here is 4. So this will be changed to 4. So 4 divided by 7 is 0.751. Here it will be 5. 5 divided by 8 is equal to 0.625. Still 5 here, 5 divided by 9, and still 5 here, 5 divided by 10. This is how we calculate the relative frequency. So in this figure, we see that how relative frequency, which is NA divided by N, fluctuates rather substantially over the occur of the first 50 replications. But as the number of replication continues to increase, like for example 1000, we see how relative frequency stabilizes. It means less fluctuations. More generally, empirical evidence based on results of many such repeatable experiments indicates that any relative frequency of this sort will stabilize as the number of the replications like n increases. That is, as n gets arbitrarily large, NA divided by n approaches a limiting value, which we call it as limiting relative frequency, or also known as long run for the event A. So this equation that you can see here, probability of A plus probability of A prime is always equal to 1. This is known as complement rule. So we say probability of A plus probability of complement A is always equal to 1. Probability of A is the probability of occurrence of A. And probability of A prime, also we can write it as like this, not A, or you can say neg A, something like that. Also sometimes like this. This is the probability of the complement of A. It means the probability that A does not occur. So this one A occurs, this one A does not occur. Then we can rearrange the equation and we say probability of A is always equal to 1 minus probability of complement A. Example here, consider a system of 5 identical components connected in a series. So 1, 2, 3, 4, 5. This is also known as cascade. In here, we say if a component that fails, S does not fail or successful, and A is the event that the system fails. It means one of them failed. So we have 31 different outcomes in A. It means SSFSS. It means 1, 2, 4, and 5 are okay, but 3 is not okay. So first one, second one is not okay, the rest 3 okay, so and so on. So there are in fact 31 different outcomes in A. However, A prime, the event that the system works, consists of a single outcome. If only this one works, all works together. So A complement, so we say A system fails. So 31 outcome is for this one, but one outcome there is only for A prime if all of them works fairly. So suppose that if 90% of all such components do not fail and different components fail independently of one another, then probability of a complement is P for the cases that all work together is equal to 0.9 power of 5 is equal to 0.59. So probability of A is equal to 1 minus 0.59, which is equal to 0.41. So we say among a large number of systems, roughly 41% will fail. For any event A, probability of A is always less than or equal to 1. This is because 1 is equal to probability of A plus probability of A complement greater than or equal to probability of A. And since we have probability of A prime is greater than 0, then we can say that probability of A is less than or equal to 1. If events A and B are mutually exclusive, it means their intersection is empty, then probability of A union B is probability of A plus probability of B. But for events that are not mutually exclusive, adding probability of A and B is called as double counting. It means we counted this part twice. That's why we have to deduct this part. So these are for mutually exclusive, but these are for there is some common area here. So here is the proof. If A union B can be decomposed into two disjoint events A and B intersection A prime. Okay, when we say A union B is this part, okay, so we can say that it can be A and B intersection complement and will be this part, right? Furthermore, B itself is the union of the two disjoint events like A intersection B and A prime intersection B. So probability of B is equal to the probability of A intersection B plus probability of A prime intersection B. Then we can rewrite probability of A union B is probability of A plus probability of B intersection A complement, which is equal to the probability of A, and instead of this one we will write this one, probability of B minus probability of A intersection B. Then this one can be written as probability of A plus probability of B minus probability of A intersection B. For any three events like A, B, and C, probability of A union B union C is equal to probability of A, it means this part, plus probability of B, so you can see we are counting twice, plus probability of C. Now we have to remove those twice parts. Then we will add at the end. So what we do, first we will consider probability of all, then we will exclude those parts that we deducted. It means we will remove this part, right? In this way, we prevent the problem of double counting. So probability of A, probability of B, probability of C, plus probability of A, B, C, it means this part, then minus those double counting. In many experiments consisting of n outcomes, it is reasonable to assign equal probability to all simple events. These include such obvious examples as tossing a fair coin or fair die once or twice, or any fixed number of times, or selecting one or several cards from a well-shuffled deck of 52 cards. So we say equal. It means we say 1 is equal to the probability of these events from 1 to n is equal to probability of 1 to n of probability of each one, which is equal to Pn. Then we can say P is equal to 1 by n. That is, if there are n equal likely outcome, the probability is 1 by n. Because the probability of occurrence of each one is the same, then we can say 1 by n. For example, a coin has only two parts, right, head or tails, and probability of each one is 1 by 2, right? So n is here 2, the number of outcome, so we have 2. Or for die, the possible outcome is 6, right? Because we have 1, 2, 3, 4, 5, and 6. Then we can say the probability of each one is equal to 1 by 6, or you can say 1 by n. These are called as uniform or equal likely. Consider an event A with this NA is the number of outcomes in N. Then the probability of event A is the sum of the probabilities of all elementary events EI in A, which is equal to the number of favorable outcomes NA divided by the total number of possible outcomes N. Thus, when outcomes are equally likely, computing probability reduces to simple counting. We can determine both the number of outcomes in A and the number of outcomes N. So we can determine both the number of outcomes in A, which occurs in event A, divided by the number of outcomes N. Suppose you roll a fair six-sided die. Fair, it means the probability of each side is same or equal. And we define an event as rolling of even number, for example, 2, 4, and 6. Then the total number of possible is 6. N is equal to 6. So the number of favorable outcome here is 3 because we want 1, 2, 4, and 6. In here, we say that the probability of A equals to number of occurrence A divided by total. How many? 1, 2, 3. So we say 3 divided by 6 is equal to 1 by 2. So we say the probability of rolling an even number is 1 by 2, or you can say 50%. And the last example, consider 6 unread mysteries on the bookshelf and six unread sci-fi books. The first 3 of each type are hardcover and the last 3 are paperback. Consider randomly selecting one of the 6 mysteries and then randomly selecting one of the fixed sci-fi books to take on a post-final vacation to somewhere. So in here, number of mysteries is 1, 2, 3, 4, 5, and 6, right? And the same for sci-fi, we can say both of them. Then each outcome is a pair of numbers like 4 and 1. And there are 36 possible outcomes. So you can see 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, and 6, and then you can say up to 6 from both of them. In here, 1 and 1, it means selecting book number 1 from mysteries shelf and book number 1 from sci-fi shelf. With random selecting as described, 36 outcomes are equally likely. 9 of these outcomes are such that both selected books are paperback. And so you can see here. So in these cases, 1, 2, 3, 4, 5, 6, 7, 8, 9. In 9 cases, both selected books are paperback. You can see here 4 and 4, 4 and 5, 4 and 6, 5, 4, 5, 5, 5, 6, 6, 4, 6, 5, 6, 6, right? So that the probability of the event A that both selected books are paperback is probability of NA, it means 9 divided by all 36 is 25%. Based on the example here, they said the first 3 books are hardcover and the last 3 are paperback. So we say both selected books are paperback. It means, so this 4 is, because this is from the last 3 here is paperback, and also this paperback, this one not, right? So these are the cases where both of them are paperback. So in this presentation, we explore the fundamental concepts of probability, starting with sample spaces and events, which provide the foundation for analyzing uncertain outcome. Also, we discussed the nature of experiment and events, highlighting their role in probability modeling. Additionally, we reviewed key set theory principles, which serve as the mathematical framework for defining and manipulating events. We then examined axioms, interpretations, and properties of probability, focusing on how probability is assigned and understood within different contexts. Finally, we covered essential probability properties, including additivity, complement rules, and conditional probability. I hope you understood the topic. Please feel free to ask me questions via this email or leave a comment below this video lecture. Thank you for your attention and see you in the next lecture.